So warm up here. An object is launched forward at 10 meters per second. At the exact same instant, an identical object is dropped at the same height. Which will hit the ground first? Explain. Y'all know the answer to that one.
They both hit the ground at the same time.
Same time, same bat channel, right? Because the only acceleration that's happening is in the vertical direction, and it doesn't matter whether it's heading to the side or falling straight down, makes no difference. It's still falling at exactly the same rate. Which will have a greater speed upon impact? Slightly different question. Yep, the launched one, right? Because for the simple reason that the one that we drop has only a vertical velocity component, but the one that we launched horizontally also has a horizontal component which adds to it, right? We looked at that in the last set of notes. So the one that we launched sideways will have a greater velocity at impact. All right, so if we launch a projectile at an angle, that means that it has both horizontal and vertical velocities initially. So typically you're not told these values independently, rather you're told the projectile's total initial velocity and the angle of launch. Okay. So if you know the angle of launch and you know the speed with which it was launched, you can actually then break that using trigonometry into two pieces, right? A horizontal component of the velocity and a vertical component of the velocity that together add up to, right, that value that you were given initially. Right? And again, that's what we call components, right? So we break down an angled motion into a vertical and a horizontal, where we can deal with them independently of each other. So example. Ball kicked with a velocity of 17 meters per second at an angle of 42 degrees from the ground, as shown in the image below. Find its initial horizontal velocity and find its initial vertical velocity. Okay. Now, of course, you know that acceleration is pulling that ball downwards, right? It is making it curve. So when we talk about where those values apply, that 17 meters per second, an angle of 42 degrees, that's immediately after impact. Remember, exactly the same way we talk about landing, right? We can't have the thing actually land and interact with the ground because that applies a force to it, right? That's going to create accelerations, and we don't want that. So we look at the point right before it lands, teeny tiny little bit. Well, the same deal here, right? Exactly as it's kicked, those are the values that we're going to use. Well, just like horizontally launched projectiles, the vertical and horizontal motion of these objects is going to be studied separately. We're going to look at the velocity in the x direction. We're going to look at the velocity in the y direction. And of course, in the x direction, horizontally, we're going to have constant velocity. It's not going to change because there's no acceleration in the horizontal direction. Now, for our vertical component, yes, we have gravity there. There's an acceleration going on. Okay? And so we'll need to use appropriate tools to find that. So when the ball is at maximum height, what is its vertical velocity? 0. Right? That's one of those things that you know because it's got to reach a point where it slows down and stops. And it stops at that maximum height and then starts back down again. Okay? So vertical velocity is going to be 0. And then what is the ball's acceleration at that point? -10. Always -10, always downwards, always good. Okay. So if you take a look at the vectors here, the green one is our velocity in the vertical direction, red one's velocity in the x direction, and the blue one is the resultant. Okay, that's the combination of the two. So vertically speaking, the ball's going to tend to slow down as it heads upwards. Okay. So So the green velocity vectors get shorter and shorter, and you'll notice at the top, vertical velocity is 0. There is no vector at that point. And then as the ball noses over and comes back down, the green arrows get longer and longer. The red arrows never change, right? Because there is no acceleration horizontally, the ball moves with constant velocity in that x direction. And then you'll notice as the green arrows get bigger and bigger, so do the blue resultants, right? Because you have more vertical velocity, your resultant vector gets larger and larger. Okay. All right. Acceleration due to gravity causes the ball to slow down as it goes up and then speed up as it comes back down. And so when we talk about projectile motions with launch angles, this is what it's going to look like. Right? Constant velocity in the x direction, constant acceleration in the y direction. And we always know that that's downwards, and it's the acceleration due to gravity, -10. Other things to know about. The amount of time it takes to get up is the same amount of time as it takes to get back down, as long as we're going to the same height. Okay? You got to watch that. So in this case, since we're kicking it from the ground, it's landing on the ground, that's not going to be a problem. Okay? And the note here says that any 2 points in the trajectory, if the projectile has an equal height, it will have equal speed. Right? So if I look at this thing 2 meters above the ground, right? Going up at 2 meters, it's going to have a plus velocity. Coming down at 2 meters of height, it's going to have a minus velocity, but the magnitude of those will be the same. That's speed. Remember, speed is a scalar. It has no direction. Right? And so we don't care about plus velocity minus. No, it's all about speed. Okay? And so that often is very, very useful. At the same height, right, it has the same velocity. Lots of little tricks here. So let's take a look at an angled launch here and start keeping track of some values. Now, these are our traditional 6, right? So we can go through and look at horizontal and vertical velocities. And unfortunately, to get some of these, we're going to have to make some calculations, and we're going to have to do a little bit of trig. Yes, it's trigonometry. Uh-oh. Don't panic. Trig's not bad. So, remember that t, that's time up plus time down. Right. So let's actually put this into practice. Cannonball's fired out of a cannon at an angle of 36 degrees, has a velocity of 49 meters per second. What is the maximum, bless you, height and range on a level surface, right? So it's going to come back to the same height from which it was fired. So the things we typically know already, there is no acceleration in the horizontal direction, and our height is considered to be 0. In the vertical direction, height is also 0. We know that the acceleration due to gravity, minus 9.8 meters per second, or again, minus 10 for the AP exam is fine. Okay. So, start breaking the problem down. We need to look at our positive directions. So we've got the gold arrow pointing up there is positive. Right? We're just going to look at this initially from launch to maximum height. Okay? Which means we're going to need some more information in the vertical direction. But if we're going to max height, what's our velocity going to be then? 0. Excellent. All right. So, little sketch here, 36-degree angle, 49 meters per second as our starting velocity. Okay. We're going to cut that down by half. Just look at the time up. Okay. And for that, we know our final velocity is going to be 0. Okay. So, we have a starting velocity at that 36-degree angle of 49 meters per second. We're going to need to use that information to break down what our horizontal and vertical velocities are. And conveniently enough, those horizontal and vertical velocities make up 2 legs of a right triangle, which makes the 49 meter per second green vector there. What part of the triangle is it? That's the hypotenuse, right? That's the C leg of the triangle. So we're probably going to have to do a little Pythagorean theoreming perhaps at some point. Remember that that should be the hypotenuse. It's the resultant, right? There are other ways you could try to draw the triangle with that being a leg, but don't do it, right? That always has to be the hypotenuse. All right, so how are we going to figure out V naught in the X and in the Y directions? Well, as I mentioned earlier, it's going to take a little trig. And there's our good friend Zocatoa, right? That's our reminder. And it says, hey, that the sine of an angle is the opposite over the hypotenuse, cosine is the adjacent side over the hypotenuse, and tangent opposite over adjacent. Okay? So in this case, our angle is 36 degrees. What side would be our opposite side? On here, what's its color, right? Is it the yellow or the red?
Yellow.
Yeah, it's the yellow one, right? That's opposite the 36-degree angle, right? And that would make the red one for the velocity in the x direction, the adjacent side. It's actually included in the 36-degree angle. All right, so to find our velocity in the x direction, since that's the adjacent side, right, cosine of 36 is going to equal our V naught divided by 49, right? So remember, sine is opposite over hypotenuse. The hypotenuse is 49, we know that. We know the angle, so if we can solve cosine of 36, which we can with our calculators, we'll just be able to multiply by 49 to get velocity by itself, and then do some arithmetic. And that's going to tell us that we have an initial velocity of 39.642 meters per second. Remember to carry some extra decimal places so that you can round at the end, and my open math won't get you. It usually works better. Okay. The other thing you need to watch out for here is to check and make sure that your calculator is set for degrees. Oftentimes they're set for radians. Okay. And that's a different method of keeping track of things. So if you're not sure how to do that on your calculator, we can talk about that at a future point. Okay. Now we can do the same thing to find our vertical velocity, can't we? Are we going to use cosine? Since we're dealing with the opposite side now we're going to use sine instead. Right? So sine of 36 is V naught y. Notice it's not V ox and voy, right? V naught in the x direction, V naught in the y direction. Work out the same deal. And our vertical velocity is 28.8 meters per second. Nice. So now we've got some pieces of information that are going to be able to help us. Okay, especially the V naught y. Okay? Because we already know that our V final, V is 0 meters per second at the top. So now we can actually start figuring out what that maximum height actually is. Okay? All right, that's x. We know our x naught is 0. We're going to ignore the horizontal for right now because we're just concerned about the y direction. Of our equations, which one seems like it's going to be more helpful? V final squared. We like the bottom one. There you go. Right, so notice we don't have time yet. Right, so using the other two is going to be a little trickier because we've got too many unknowns. So the V final squared equals V initial squared plus 2a, and then x minus x naught, or delta x. That's our change in height. And since we know what x naught is, it's 0, then that value just becomes x. So, right, x naught's 0, so we can just drop it out. Okay. We know V final, we know V initial, we know a. We just need to find x. So let's do some algebra. subtract our v naught squareds from both sides. Okay. So v final minus squared minus v initial squared equals 2ax. Divide both sides by 2a. That'll solve for x on the right-hand side. And now we have v squared minus v naught squared over 2a equals x. Okay. So now we've got the equation we can use to solve for our height, x. Now we just got to plug in some values. It's time to substitute. So v final squared is 0, so that's easy. V initial, 28.8 squared. And then we have 2 times minus 9.8, remember, downwards. Okay. So we're going to get a negative value in the numerator, a negative value in the denominator. Those negatives will cancel each other out, and you'll end up with a positive value. Okay. And in this case, that positive value is 42.32 meters. So that's our maximum height. We can't get any taller than that based on that initial velocity. Okay. So what else can we do with that? Well, we're eventually going to want to find range. So you might want to think about how to do that for just a second. Any questions before we move on here? Not too big a trick. The only really new thing we saw here was the use of the sine and cosine trig functions so that we could take our resultant vector, the velocity with which we fired the cannonball, and use that to figure out what the vertical velocity was, what the horizontal velocity was. Okay. So now we want to consider the range part of the question, right? And to be able to calculate that for our cannonball, we're going to need to know time. Okay? So can we get time from the horizontal here? Not so much. Right? So we're going to need to go back to the vertical direction again. And there's that note. Find time using vertical data. And in this case, since we know our starting velocity, our final velocity, and our acceleration, it's easy enough to just use v equals v naught plus at to solve for time. Right, so move the v naught over to the other side, divide by a, plug in our values. Okay. Notice again, we're going to get a negative over a negative, so we'll end up positive for time, which is good. Negative time has no real meaning. So if you're coming up with a negative time, you've got a sign error somewhere. And so we end up with this at 2.94 seconds. Now, as the note says, this is only for half the motion because we only considered from firing to peak height. That's halfway there. So to get the time up and back down, what do we have to do? We got to double it, exactly. Right? So time up and time down are the same, so 2.94 up, 2.94 back down, as long as we ignore air resistance. Right? Again, it's assumed that we're doing that here. So our total time is now 5.88 seconds. And since time is the same for both the horizontal and the vertical motions, we now know it for the horizontal too. Right? So now we can consider our range, and since we know what our velocity is and it doesn't change because there's no acceleration, we know what our time is. Right? Which equation do we like here? Yeah. How about that middle one? X equals x naught plus v naught t plus 1/2 at squared. The fun thing about this, of course, is that since a is 0, that entire last term just disappears. Bam. And so there's x equals x naught, which is 0, plus v naught times t. We figured our v naught earlier, 39.642. That came from cosine of 36 times the hypotenuse of the triangle, 49 meters per second. And then we just know the time is 5.88, so let's do a little arithmetic. And our range on this cannonball, 233.01 meters. So like we talked about in the last notes, we oftentimes have to work our way back and forth between vertical motion and horizontal motion to get things we need to solve for the specific values we're looking for. So we figured the horizontal and vertical velocities, used the vertical velocity to find height, which was the first question. Used the vertical direction again to find time to get to that height. Doubled the time since we were calculating just on the way up. Coming back down, adds another 2.94 seconds. And then once we know the total flight time, then we can calculate how far it's going to go in the horizontal direction. Okay? So there's a lot of moving parts to these, right? But fundamentally, if you keep your eye on what you can solve and what you need to solve for, these usually aren't too bad. All right, any other questions?